All right, continuing on with our Chapter 4 lecture videos. And you'll have to forgive me, but my handwriting might be a little bit sketchy today. Kind of shaky, but we'll see what we can do. But we're continuing on with using molarity, all right? And we're just going to keep doing practice problems because the more ways that you can see these problems worded and the different types of questions, the better you'll get at things. So with this question, we want to answer how many moles are there in 750 milliliters of 2.15 molar hydrochloric acid solution. And then just to remind you, whenever you see this capital M, that means that you're dealing with molarity as a conversion factor. Okay? So that means that our 750 milliliters is our given information. Remembering that molarity is the units of molarity are moles and liters. Right now we've got our information in milliliters, so we need to make sure that our units match. So I'm going to convert my milliliters to liters first. And there are 1,000 milliliters in 1 liter. So we get 0.750 liters of HCl. Right, now that I've got my units matching my molarity, I can use the molarity as a conversion factor. So I'm going to start with the volume. And I'm going to write my molarity such that my liters end up on the bottom. Moles of hydrochloric acid per liter of solution. So I'll find out that I have 1.61 moles of hydrochloric acid. So now that we have this ability to go between volume and moles, we can start to do stoichiometry with this situation. Okay, because it's all about the mole bridge, right? So now we simply have a new path to get to moles, right? We've already done percent mass, and we've done molar mass, and now we're doing relationships to volume and solutions, but it's all a means to get to moles. Right? So let's say, for example, I start with a volume of compound A or solution A. I can convert that to moles of A using molarity. Once I know compound A, then I can convert that to moles of compound B using a mole ratio. And then once I know compound B, I can do anything I want with it. If I want to convert, for example, to volume of B, I use that molarity. Right, this would be moles of A, this would be moles of B. Okay, but the important step, because we're doing stoichiometry, is the mole bridge, the mole ratio. Okay, so it's all I have to do is get to moles, and then I can convert moles of A to moles of anything else in the equation. All right? So let's do some practice with this idea. So here's our question. What volume of 0.15 molar potassium chloride solution is required to completely react with 0.15 liters of 0.175 molar lead nitrate. So we must have a reaction equation. All right, we need a reaction equation because we must have mole ratios. And the only way we're going to get a mole ratio is if we have a reaction equation. Right, so we're given that we have a solution of potassium chloride aqueous, that says AQ there. I warned you that my handwriting would be a little sketchy. And we're going to react it with some lead nitrate solution. So I'm going to do a double displacement reaction. I'm going to put the potassium with the nitrate and the lead with the chlorine. And I know that this is lead 2 because I have 2 nitrates, and each of those nitrates is a 1- charge, so I know that this is lead 2+. So my product will be lead chloride and potassium nitrate. And then I know from my solubility rules that the potassium nitrate is aqueous because everything with potassium is aqueous and everything with nitrate is aqueous. And then the lead chloride, I'll look that up in the potassium or the solubility rules. Or more correctly, I will have that memorized so that I can just know that the lead chloride is a solid, because chlorides are usually soluble except with silver, mercury, and lead. Okay, so chlorine with lead will make a solid compound. And then I need to balance it, so I have a 2 to balance my nitrates, and then I need a 2 to balance my potassium and my chlorine. Okay? So now that I have a reaction equation, I know my mole ratios, and I am given in my problem that I'm reacting potassium chloride, and I need to know how much potassium chloride will react with the lead nitrate. So I'm looking specifically at the mole ratios between those two things. So now let's sort of suss out what information we have in this problem and how we're going to tackle it. All right, I told you anytime that you see the capital M, that molarity, we've got one right there and we've got another one over here. Then you're going to use those as conversion factors. Okay? I'm not going to start with the molarity of the potassium chloride or the molarity of the lead nitrate. So I'm going to look for the thing that I have the most information about. Right? So for the potassium chloride, all I have is the molarity. For the lead nitrate, on the other hand, I have volume and molarity. If I have volume and molarity, I can use that to convert to moles. So I'm going to start with the 0.15 liters of lead nitrate. And again, I want to emphasize the importance of using labels on everything, because when we get into these types of problems, you're going to want to make sure you're keeping track of what you're doing a calculation of. Okay, so 0.15 liters of lead nitrate. So I'm going to use that molarity for lead nitrate to convert that to moles. And I have 0.175 moles of lead nitrate per liter of lead nitrate. Okay, so my liters of lead nitrate will cancel, so now I'm at moles of lead nitrate. And I need to get to potassium chloride, so I'm going to use a mole ratio there to get to moles of potassium chloride. So from my equation, I have 2 moles of KCl for every 1 mole of lead nitrate. So my moles of lead nitrate will cancel. So now I have moles of potassium chloride. Now the question ultimately wants volume. So if I have moles and I have molarity, I can use that to convert to volume, because molarity is all about volume and moles and volume. All right, I'm going to have to come down to a second line because I'm about out of room here. So moles are on top right now, so I'm going to put moles on the bottom in my next step. All right, so my moles of KCl will cancel moles of KCl, leaving me with volume of potassium chloride, which is ultimately what I am after. Okay, so we're still doing stoichiometry, just like we did in chapter 3. The difference is that now we have a different way to get to moles and a different way to get out of moles. But ultimately, it's just about that mole ratio in the middle. Okay, so I'm going to go ahead and stop this video right here, and we'll pick up on the next video talking about dilutions.